two functions we want to graph. So this is the form y equals a f of x plus 4. We had like a x minus 3 or an x plus 5 up here in the exponent. Then it'd be an a f of x minus h plus 4. I always want to think about this because we're going to have it and have to know it real well by the time of the final. Okay, so a equals 3. The vertical stretch factor is 3. A equals 4. Vertical shift is 4, and f of x, of course, equals 2 to the x. Well, we start with the graph of 2 to the x. And whether you're in my class, pre-calculus class or not, I'm going to recommend, unless your instructor forbids it, that we start with a 4x4 box. Now this looks wider than it is high. We're not confined to using the same scale for the x-axis as for the y-axis. And actually, I should have drawn that a little. Let's do that again. And just draw it lower. Okay, so just for scale, this line is x equals 2. This line is x equals -2. The graph, if it's constructed, well, going to be close to the x-axis here. This is a line x equals 4. That y equals 4, sorry. So that x equals 1 would occur about here. X equals 4 up here. And you can verify just with the table. As the graph goes through the point -2, 1/4, 0, 1, and 2, 4. I'll label those. It's unnecessary for students in my class, but the intercept here is 0.01. And this point is the 0.24. And we already have enough of the exponential function to see what we need to see. Okay, now, if we vertically stretch this by a factor of 3, then all the y values are multiplied by 3. So y equals 4 becomes y equals 12. And we'll make a note that the vertical stretch moves the y equals 4 line to y equals 12. So that's why we have the y equals 12 line. And then our rectangle, which I'll draw in slightly different color. You know, more than slightly, these all white. White isn't even a color, is it? Okay. So there we have the rectangle in which we would construct the graph of 3 capital X. Okay, so every y coordinate is going to be 3 times as great. And if you vertically stretch this whole thing by a factor of 3, this point's going to go 3 times as far from the x-axis, so is this one, and so is this one. This point is going to move up to about here. This point is going to move up to about here. And this point is going to move all the way up to here. And just by moving those points 3 times as far, the 3 points that I have here, moving those points 3 times as far from the x-axis, get a good picture. And that's going to be the graph, the function y equals 3 times 2 to the x. That makes sense? Should make a lot of sense. Think about it until it does. Okay, now, then we've got to do the vertical shift of 4 units. That means every point goes up 4 more units. How far is 4? On the y-axis, 4 is this far. So every point goes up this far. This point will go up to about here. And this point will go up to about here. And this point will go up to about here. Now we draw another box. I don't want to draw over my pretty blue line. And I'll draw one close to it. This is a new box. Okay, so we started with the white box down here. We stretched it by a factor of 3. We got the blue box. Then we moved the blue box up 4 units, and everything moved up 4 units. And of course, this is all consistent with these 3 points. And right here, is y equals 3 times 2 to the x plus 4. The line y equals 4 is an asymptote because, of course, as x approaches negative infinity, 2 to the x approaches 1 over 2 to the big number, which would be a tiny number. So your final graph, guessing it is to just a little different scale, because I don't want to go up into this. We have the line y equals 6. We have a curve comes along here, asymptotic, negative x-axis. It goes on up like this. This point would be 4, 16. This point would be 0, that would be 9. And sorry, 0, 7. And we'll have a point over here that would be negative 2, 6 3/4. I'm not going to bother labeling it because right there we see pretty well what the scale of the graph is. And when you draw the graph, you want to, instead of labeling this, you just say, here's a line x equals 4. And here's the line y equals 16. Now we can see in the line y equals 6. It doesn't have to be the x equals 4, y equals 16. and y equals 6 line. But if you think of starting with a 4x4 rectangle, that's easier. Okay? And I think that gives you a really good handle on how to sketch a reasonable graph with this. Okay? And everybody that did this did a good job with it, but a little more detail lets you look at it and understand what the numbers are like. Okay. Just the x equals 4 line and the y equals 16 line define the scale of this graph. We don't need to rule it off into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You want to go to x equals 10 anyway, because at x equals 10, this is going to be 3076. So where's 3076 on this scale? It's high enough that you certainly wouldn't want to fall from there. Okay. You had a parachute, you might survive it, but okay, anyhow, get the idea. Then you don't have to number 1, 2, 3, 4, 5, 6, 7, 8, 9, up to 16. Once you got 16, if you want 6, you can tell about where it is. If you want to divide it up, you can divide 16 and 2, right there's 8, so there's 6 and all that stuff, okay? And we've done a lot of that in my class. In other classes, you know, you use what you're permitted to use. But I strongly urge people to do these sketches and stick with you, especially if you've got more math in your future. Okay. Now, y equals -2 to the negative x plus 6. So now here's board space. I'll start here. We'll use some more board space. Y equals 2 to the negative x. Just a quick picture. It looks like this. Because when you replace x by negative x, you flip things around the y-axis. X becomes negative x. So if at this point you have the point 2, 4, then 2 to the negative x will give you the point -2, 4. Okay. So that your rectangle flips. So I'm not going to try to draw that because it's going to be the same rectangle, it'll be a little bit clumsy. Okay. Then y equals -2 to the negative x. Well, if you put a negative in front of 2 to the negative x, that takes the y values of this graph and makes them negative. So for example, this point would come down here. The y value would become negative. And this point would come down here. The y value again would become negative. And this point here corresponds to this point. And you don't have to make a table to understand if those are the points of the graph. Remember, in my class, at least, we constructed the graph without ever talking about numbers. And we used the numbers to see what the function ought to be. Now, if you're in another class, you probably make tables. Well, you should know that just use -2, 0, and 2. You don't have to fill in all the other values in the table because the curve is so well defined by any 3 points on it. It's almost obvious. You almost can't draw the curve wrong. Well, yeah, you can. But if you do it a few times and compare with the actual picture, you'd be very good at drawing the curve. Not better than these curves I've drawn. These are just kind of approximate sketches. But there is -2 to the negative x. And you know what I did over here? I was writing this, I saw the 6. Let me fix something. This should be the line y equals 4. And this should be the 0.05. Okay. I got the 6 into my head because my eye caught it. I didn't have a good filter. Okay. I didn't realize that until I looked, okay, now we raise this one up 6 units. I said, wait, we raise that last one up 6 units. So, okay, anyhow. So what do we do here? We raise this up 6 units. Well, if this is y equals -4, then the graph we get is going to be something like this. Now this y equals 4 goes with this graph, but there'll be a y equals 4 that goes with this graph. Well, we've raised this graph up 4 units. This graph has an asymptote to the x-axis, so we got to raise the x-axis up 6 units. X-axis is the asymptote here. X-axis is the asymptote here. And now we raise it 4. There's our new asymptote. So we take this shape and we raise it up 4 units. This point would be like -1, so that point's going to go to like here. And we don't worry too much about what the other points go to. We want to just get the general picture of what specifics. Yeah, we did kind of worry about that. I should be a little steep there, but you get the idea. Okay. Now I think one person had all the graphs right, had this one, but it was reversed because might have missed that negative. There are a bunch of negatives in there. It's real easy to miss a negative. And look, if you had it reversed, you understand why you get it. Actually, no, you're okay with this negative, you missed that negative. Okay, is that flipped it? I think somebody did that. But you know, everything else they'll look real good. So I think people have some evidence of having learned something from the homework. Okay. Okay. So that's a little bit about constructing these graphs. We want to go on though and move into logarithms. And let me just double check the calendar. If I can find the darn thing. Looks like I don't have a calendar. There, I've got one. What mental illness is it that causes people to write black on dark bread? And people are trying to be edgy and taking it too far. Okay, now, right now, your assignment has rational equations. And I'm going to make a change and put rational equations later. And I'm going to move logarithms there. And oh boy, that's tricky. Let's see. Still recording, so it shouldn't be recording. Okay, when I looked ahead, there was an assignment. The assignment after the next one was kind of out of order, so I fixed that. Okay. So can you write me the table for the inverse function? And it was going to be, just wanted to make sure every once in a while it goes wrong. Okay. Oh, wait. Yeah. Okay. The table for the inverse function just reverses because the columns, because the inverse function reverses x and y. That's what an inverse function is. It's not plug in, write the equation for the function, and then replace all the x's with y's and all the y's with x's. It's you switch x and y. Therefore, you write x wherever there's a y and y wherever there's an x. If all you know is what you do with an equation, then you don't know what to do with a table, which is switch x and y. Same thing, same rule. So I recommend that you remember the inverse function, switch x and y. Now, there are things about domain and stuff that aren't going to be relevant here. Sometimes you get something that isn't a function when you do that. And then you got to choose a branch, but you've seen all that. Okay, so anyhow, we switch x and y. Now we still use x for the first column and y for the second column, because that's the way we understand tables. That means y values appear as x's now. And your x values are going to appear as y. Okay, sketch me a quick graph of that. Now, if I'm trying to draw the points on this graph, I see that x goes out to 4, right? So I better have a line for x equals 4. So that means I'm going to have to extend out here. This is 4 units, and I've got to extend out to here. Okay, so I got the line x equals 4, which I'm going to need. Then I'm going to need y equals -2. Well, let's see, if that's 4 units, 2 units is about here, so y equals -2 would be down about here. And then y equals 2, of course, you just subdivide, take this line twice as close to the origin, the x equals 4 line, take it twice as close to the origin, you're going to get x equals 2 line. So here's your x equals 2 line. Then you're going to need x equals 1/4, 1/2, and 1. Well, here's 2. So x equals 1 would be about here. X equals half would be twice as close to the origin as x equals 1. And x equals 1/4 would be here. So you want to draw lines for what you got. Okay. And then, of course, y equals -1 would be halfway between the x-axis and the y equals -2 line. And x, this should be y equals 1. Right. So we got the lines y equals 2, y equals -1, y equals -2, -1, y equals 0 is the x-axis, y equals 1, y equals 2. And now we can sketch the points. And we connect them with a graph. Connect them with a curve. Well, I attempted to do the same thing over here with an equal scale, so I could show you something, and never could get this curve to have as much concavity as this curve. Should have been working in the middle of the board. I might have been able to see it better. Anyhow, we draw the y equals x line. And as you've seen for inverse functions, if I have a good y equals x line, and I don't, comes a little lower than that, still isn't very good. But this point matches up with this point because this is a point 2, 4. This is a point 4, 2. The x and y coordinates have been reversed. Similarly, this point is 0, 1. This point is -1, 0. And the other points. These points match up with the points that you could get if you did a full construction with this table of the 2 to the x function. So if I say, I do the same thing, y equals x line should make a 45-degree angle with the x-axis, but since my y scale is squashed down a little bit compared to my x scale, it didn't quite work out. But you do the same thing up here. These points correspond, these points correspond. And if the scales are equal, y equals x line makes a 45-degree angle with the x and y axes. And a line connecting any 2 of these corresponding points will make a right angle with that line. And that line will cut this line in half. In other words, this will be as far on one side of the y equals x line as this is on the other. And your text will show you a good picture of that. Okay. Apparently I'm not capable of doing a good picture this morning, but you get the idea. Your tables look good and use other graphing techniques to graph them. Okay, so this is y equals 2 to the x. What function is this? Y equals what? Well, if you do the inverse of the squaring function, you're going to get the square root function. Okay. If you do the inverse of the cubing function, you get the cube root function. And we know what those functions are. If they're power functions, we know what to call them. Inverse of the exponential function, we got to make up a name. Now, back, I don't remember, 300-400 years ago, they asked me, they wanted to know what names, they came and asked me. Okay, I said, this is, call it log. Okay. Logarithm. Seriously, I don't know where the name came from. This is log sub 2 of x. How to read that log base 2 of x. Okay. You can calculate the log base 2 on your calculator. You have two log keys on your calculator. I think one's a second function of the other in most calculators. You have the log log, which is just a log base 10. Okay. And incidentally, we could also do log base 3 of x over log base 3 of 2. Okay, let me come back. Log log is log base 10. That means you would invert the function 10 to the x. Well, that function gets out of control real fast, but it's an important function because powers of 10 are important. Okay, makes sense? So the ln is log base e. Now we could have done this with 3 to the x. The numbers would have been more manageable, and we did the graph of 3 to the x. You could invert the graph of 3 to the x, you'd have a log base 3 function. And you should know what I mean. You know, log base 2, log base 3, or 2 to the x, 3 to the x. And e to the x is in between there. Haven't defined e yet, but I probably will in pre-calculus class. Okay, e is a number between 2 and 3. It's about 2.7, 2.7, 182, all that stuff. Okay. You have a button on your calculator for the log. So you can do ln x over ln2 or log x over log2. It doesn't matter which you do, you get the same result. Okay. That's the first thing you got to understand about calculating with logs. And this is a place where you will need your calculator. And any calculator that does even square roots will have logs on it. Almost any calculator. Okay. The inverse function any base. Base could be 10 on this log, it could be e on the natural log. If it's anything but the base 10 or the natural log, we got to put the base in there. If it's base 10, we don't have to write base 10. That's what log means. Usually, sometimes it just means natural log, but ln means natural log. We don't have to write a base e. We could write that as log base e. Okay, well, what does log base b of c equal a mean? Let's look over at the table. Log base 2 of 1/2 is -1, right? Why is the log base 2 of 1/2 equal to -1? It's because 2 raised to the -1 is 1/2, right? So this is like log base 2, log base b, base is 2, of 1/2 is -1, right? So this is equivalent to the a equals c. Again, if c is 1/2 and a is -1, then you would write b to the -1 equals 1/2. b is 2, 2 to the -1 equals 1/2. Okay, think about that. Look at the table. Think about this equivalence, because this is a key to solving exponential and logarithmic equations, which are very important. It's another equation solving tool. There are also rules for logarithms. We'll probably talk about that. Let's solve an equation. Just to show you this is kind of powerful. You've estimated things like this curve, if x equals 1.5. Sorry, if y equals 3, it's halfway between 2 and 4. Here's your y equals 3 line. And I don't think anybody can see this. It's looking at the video. Okay. Here's y equals 3 line. Where that line intersects the graph, we get an x value. What does that x value look like to you? Well, we've done a lot of estimating. Pretty good at estimating, but here's the x equals 1 line here. Here's the x equals 2 line. We're between x equals 1 and x equals 2. It looks like maybe a little closer to x equals 2. Maybe it's x equals 1.5, but I don't think so. I think it's about x equals 1.6. I think it's a little closer to this line than this to this line. Now, those lines aren't perfectly straight, so we could be off by a bit. Because of the way the curve goes, concavity of the curve, we know it's not exactly 1.5. Remember, 3 is halfway between 2 and 4. We could, if it was a straight line, it would make this point halfway between 1 and 2, which would be 1.5. But we're going to figure it out. Okay, so estimating y equals 3 on the 2 to the x graph, we can now solve to the x equals 3. This is b to the a equals c. B equals 2, a equals x, c equals 3. Right? If b is 2, then you got 2 here. If a is x, then you got x. That's 2 to the x. And equals c equals 3 equals c. So for these values of a and b, that's this equation. Okay? So those values of a, b, and c, what is this equation? I'm going to erase this graph. It's not all that great. We got that one over there anyhow. You write it down? Let's see if you write it down. Just want to see if you're understanding. Okay, well, this is b to the a equals c with a, b, and c equal these numbers. It's equivalent by what I said here and by what I at least demonstrated and claimed that this is equivalent to log base b of c equals a. Well, b equals 2, a equals x, and c equals 3. That gives you log base b, which is base 2. C is 3. C is 3. A is x. Now, how are you going to get that value in your calculator? Write out what you would do to get this value in your calculator. It's there on the board. Let's see if you can find it. Okay, well, how do you get log base 2 of 3? Either you make a really, really good graph and make a good estimate, or you use this. And it should be 3. Okay, well, I wrote that so badly, but have it all smudged out. I'll make sure everyone can see it. It's really important. Okay, so this is natural log of 3. The natural log of 2. Or log of 3 or log of 2. The calculator will probably let you even write in log base 2 of 3, so you don't even have to do this. But I don't want to see it. Okay. I want to see this or this. And then you calculate this. Okay, well, I'll give you the mystery what the number ought to be. I estimated 1.6. Nobody seems to have their calculator handy. Starting next time, you probably have your calculator handy. You got to use it on your homework, right? Okay.
Oh, yeah.
Okay. Now, how about five to 3x minus 4 equals 47? First of all, what power of 5 equals 47? Well, it's between 5 squared, which is 25, and 5 cubed, which is 125. So it's probably closer to 2 than it is to 3, probably around 2.2 maybe. So this 3x minus 4 would be somewhere between 2 and 3, maybe around 2.2. Okay, maybe around 2.3. When possible, you should give it that sort of thought. 47 is not that high power of 5. You know, well, anyhow, whether you do or not, we can translate this. Can you translate this into this form? Fill in the blanks. This b to the c equals b to the a equals c, with b equals what, c equals what, and a equals what? Okay, well, easiest thing to identify is often the exponent, which is 3x minus 4. I didn't leave myself room to write out 3x minus 4. Let's go ahead. We know we got to identify A, B, and C. So let's C is 3x minus 4. Sorry, A is 3x minus 4. The easiest thing to solve identifies the exponent. Then it's easy to identify the rest. The base is whatever you're raising to the power of the exponent. So the base is 5. And the only thing left is 47, which has to be on the other side of the equal sign, and there it is, okay? Equal C equals 47. So this is equivalent to, that's a double arrow. It means if this is true, then that's true. And if that's true, then this is true. It's not an equal sign. Equivalent to what? Write it out in log form if you haven't already. I'm just going to take a quick look. Yep. 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 I think so. A couple of those things are a little hard to read, but saw everything about why I tended to what I expected to. Let's just be sure. That's log base 5 of 3x minus 4 equals 47. And I wrote that wrong because I wasn't thinking. Looking towards base, anything else. Log base 5 of C, which is 47, equals 3x minus 4. Didn't need to worry there. Okay, can you solve that equation? Well, we need a little more board space, so let's take again. 5 to 3x minus 4 equals 47 is equivalent to log base 5 47 equals 3x minus 4 by this equivalence. First of all, let's write 3x minus 4 equals log base 5 of 47. Then we're going to add 4 to both sides. We get 3x equals log base 5, 47 plus 4. That's a bad looking 4, make it a little worse. Okay. And then there's our solution. Now, if you want the number, you go to your calculator. I guess we could write one more step. Equal log 47 over log 5 plus 4 all divided by 3. You punch that into your calculator correctly, you're going to get a good result. And you can check that result. Put whatever number you get here into 3x minus 4 and see if you don't get something between 2 and 3. In the comments I made before. Okay. Because the power of 5 that gives you 47 is 3x minus 4. the power of 5 that gives you 47 is between 2 and 3. That would be very useful to remember and to think about when you do the problems. Don't just do and be satisfied that you have the right solution. Think a little more about them. It doesn't take long, and it deepens your understanding. Gives you more power to do well on a test, or when you're trying to apply this also, you're going to retain it better. And you are going to need it if you go into any kind of a calculus course. Okay. And it's easy. That's the nicest thing about it. With a little practice, it's way, way, way easier than graphing rational functions, for example. Okay? Just cut and dried.